There we go. Okay. Hey, I'm Ryan. Here today talking about space, specifically nebulae and the birth of stars. I went to CCSU to interview an astronomy professor. Here she is.
My name is Dr. Christine Larson. I'm an astronomy professor here at Central Connecticut State University, and I've been on the faculty since 1989. So a nebula is a cloud of gas and/or dust in space, and the word nebula actually means cloud in Latin because everything sounds smarter when you say it in Latin. Rather than just saying cloud, it's a nebula. And between the stars, we have these floating clouds of gas and dust. They are normally associated with the births of stars and the deaths of stars. And the universe is really great at recycling. So the nebula that is left over from the birth of a new star will dissipate into space and join in with the material from the deaths of other stars and then be recycled into a next generation of stars.
Now that we have some basic information about nebulae, I then asked a question about how the deaths of stars cycle into their birth.
So the deaths of stars depends upon their lives, which kind of makes sense. All stars are pretty much made of the same thing. They're about 3/4 hydrogen, the lightest element in the universe, and of the remainder, most of that quarter is helium, the second lightest element in the universe. And everything beyond hydrogen and helium on the periodic table, over 100 elements, is a really tiny portion. In terms of, for example, our sun is only 2% of that other stuff, which is really important if you're making things like planets and bunny rabbits and penguins and bowling balls and stuff. But for stars, it's really the hydrogen and helium that's important, because stars, over their lives, mush together. They do nuclear fusion. They fuse together the hydrogen into helium, and that's how stars shine. But it only happens in the core of a star because that's the only place that's hot enough and dense enough to sort of coax those hydrogens together to fuse into heliums. So when a star runs out of hydrogen in its core, it can still have plenty of hydrogen left over, but it's the core where the action is, and the star starts to die. And over the next millions or billions of years, depending on the mass of the star, it may go through a bunch of different fusion reactions, and the helium can convert into carbon, and the carbon can convert into oxygen. And for stars like our sun, that's the end of the road. Our sun will not be able to fuse anything heavier than that because it doesn't have enough gravity, because it's just not heavy enough. And so when a star like our sun dies, all of that extra hydrogen that never got to fuse gets puffed off into space as a nebula, a specific kind of nebula that we call a planetary nebula. They sort of look round and greenish to the human eye like planets do. And that material will be recycled into the next generation of stars. Now, the core of a sun-like star will actually implode and will actually become about the size, physical size of the Earth. If you can imagine a really, really compressed ball of carbon, kind of like a super diamond. And that's what we call a white dwarf. Now, stars that are heavier than the sun, they can fuse heavier elements and go further down the periodic table, and they can make elements down to iron. But no star can fuse iron. And so if a star is heavy enough and can get all the way down to iron, that's the end of the road, and the star explodes as a supernova. And the shrapnel left over from that explosion is a different kind of nebula called a supernova remnant, and that has an incredibly rich chemistry, because the energy from the explosion goes into a giant fury of fusion and makes all the elements on the periodic table that are heavier than iron.
Then I asked how nebulae formed stars.
Those are the kinds of nebulae that are associated with the deaths of stars. So fast forward millions or billions of years, all this leftover material is moving through space. It aggregates with other nebulas from other dead stars and forms what we call a giant molecular cloud, sometimes called a giant molecular complex. And this is something which is maybe 1,000 light years wide, and it has enough material to make hundreds of stars. So think of this sort of like you're going to the store and you have to make cookies. And you're like me and you're lazy and you're not going to make them from scratch. So you get that Pillsbury log of cookie dough, right? And it's sort of an amorphous blob. And somehow you've got to make cookies out of it. Well, that giant molecular cloud is like that log of Pillsbury dough. It could form cookies under the right circumstances. But you don't want to make one giant cookie because that would be a big failure, right? It wouldn't cook right in the oven. So what you want to do is you want to take that Pillsbury cookie dough and you want to pinch off and make individual cookies, right? And if you pinch off too much, it's not going to cook. It's not going to be a good cookie. But if you pinch off too little, it's not going to be a good cookie either, right? So there's a range of, you don't want to be smaller than this, and you don't want to be bigger than this. Same thing happens in a giant molecular cloud. But instead of a giant hand pinching the cookie dough, it's the hand of gravity, which is taking bits of the gas and dust in the nebula and smushing them together. And if gravity tries to get greedy and make a really gigantic star, it'll actually explode when it tries to form. That's no good. And if gravity is too timid and pinches off too little a piece of the nebula, it won't actually get hot enough to do nuclear fusion. So it's really like making chocolate chip cookies. You gotta pinch the right amount of material so that it can bake well and become the cookie, become the star that you want.
Then lastly, I asked about the different types of stars formed in nebulae.
So because there's a bit of a range into how big a star can be, I mean, it can't be too small, it can't be too big, stars come in different sizes. By different sizes, we mean different masses. The smaller ones, the ones that are maybe 1/10 the mass of our sun, they spend their lives sort of being very fuel efficient. They're dimmer than our sun, they're cooler than our sun, but they live a lot longer period of time. Our sun's lifespan is about 10 billion years in total. Imagine a star that is maybe less than 1/100th as bright as our sun, but can live for 100 times or 1,000 times longer. Very different kind of star. We call those M dwarfs. On the other end of the spectrum, you've got the overachievers, right? You've got the fancy sports cars that don't get very good gas mileage. So if a star is born very massive, it's very hot and very bright and, stands out, but it doesn't last very long. The lifespan of that star might be as little as 10 million years. Now, 10 million years is a lot longer than you or I are going to live, but if you think about it in terms of the evolution of planets and the evolution of life, that takes a really long time. If a star has a relatively short lifespan, it's not going to be around enough for planets to organize or for life to evolve on any planets that happen to be around that. So there's kind of a sweet spot in the middle of stars that are not too bright and hot, because you don't want to fry your planets, and you also want to live long enough to give enough time for some interesting geology and biology to take place.
To conclude everything, a nebula is a cloud of gas and dust collected from the debris caused by star death, which is then smushed together by gravity to create stars. Stars are the pressured combination of hydrogen and helium, the two lightest elements in the universe. Their deaths release the remains of the elements along with any planets destroyed in their explosion that can also be known as a supernova, that is collected into a nebula. There are many different types of stars and nebulae that have different purposes and capabilities. Some nebulae are planetary, which form from the death of stars, or there's emission nebulae, which are called the pillars of creation, for the creation of stars. Special thanks to Dr. Larson, Director Ivers, and the rest of CCSU. Thank you for watching.